Okay, calculus, here we go into section 1.5 and kind of reminding you of the theme of chapter 1, which is there really isn't a theme. This isn't terribly well related to anything that we did in any earlier sections. It's just something else that your author thought would be a good idea to refresh your memories on a little bit as we walk through the rest of the year. So we start talking about inverse functions, and in my recollection right here, you guys may or may not agree with this, inverse functions is one of those things that people generally understand the definition to pretty well and pretty easily, but don't always understand how to apply that definition and what it actually means from a practical standpoint. So the definition of inverses, it's one of those things that's very messy to actually write out, and so this is what I've come up with right here. So two functions, f of x and g of x. Now, I wrote this in such a way so that g of x could also be rewritten here as f inverse of x. The smartboard type here doesn't look real good. That's supposed to be basically an exponent right there, or at least it's supposed to look like an exponent. It's really a superscript, but I wanted to make a point in saying that that is not an exponent right there, which I think you guys knew anyway. But back to the definition. So two functions, f and g, or the inverse of x, are inverses of one another if for every single point a comma b that's located on the graph of f of x, the inverse of that point, which would be called BA, is on the graph of g of x, which of course is the same as f inverse of x. And then what we have down here in purple is a much more concise way of saying the exact same information. If f of a is equal to b, then g of b is equal to a, meaning that if a is an input value into the f function and b is the output value that results, you can take that output from f and make it the input value into g. And if these functions are inverses, the output value you'll get from taking g of b is going to be a, which is the same as the input value that you used into f. So one of the phrases that people lose track of right here is the phrase the inverse of a point. It's in that same category of things like reciprocal, and a reciprocal of a fraction is something you guys know very, very well. But the inverse of an ordered pair, everybody, is when we simply take the x and y coordinates of an ordered pair and we flip those around so that the x becomes the y and the y becomes the x. And if two functions have this relationship, that every single ordered pair in the set of one function out there, if its inverse falls in the second function, then those functions are going to be inverses of one another. So let's play around with that idea just a little bit. And so I wanted to start with two very, very simple functions that I think you guys know are inverses of one another. And we'll talk about how to find inverses in just a second, although I think you guys probably remember that. All right, so let's take a look at the first one right here. F of x is equal to x cubed is a parent graph you guys should know pretty well. Passes through the origin, and it's a cubic function. So we've got the point 1, 1. We'd have the point 2, 8. Basically, guys, this looks like a parabola. It's not. It looks like a parabola. It just increases more quickly into that first quadrant. However, the difference then is here with x cubed, when we put in negative values in for x, we're going to get negative values out as well. So this one's going to go into the third quadrant with a -1, -1, a -2, -8, and so on. So y equals x cubed, or I should say f of x equals x cubed. That's how we've named it here. That's going to be the function that we're starting with. Let's go ahead and talk about this, even though I don't think it's something that you guys need a whole lot of work on. How to find the inverse of a function? It's a two-step process, everybody, and the first one is super easy. You take the original function right here, think about the f of x just being written as a y, and your first step then is going to be to switch the x and the y. So instead of y equals x cubed, we're now going to make this x is equal to y cubed. And technically right there, you're done. You've found the inverse of the original function. But it's a convention now that we generally like our functions solved for y in terms of x. So now at this point, pretty simple one here, we'd get rid of a cube by taking a cube root on both sides here. And we would end up with y is equal to the cube root of x, and that's the inverse of the original function f. Now, one thing we're going to get used to in this section, and that is, everybody, that we have to respect what it means to name a, let me use the word relation right now, but to name a relation with function notation. There are lots of relations out there in the world that are not functions. Okay, but only the ones that are functions can be named with function notation such as f of x or g of x. So when we get to this spot right here, you'll see this in a few problems we're going to do pretty soon. When you get to this spot right here, you've got to try to determine whether or not this new relation is a function. If it is, we probably want to take the time to rename it instead of y by calling it something with a proper functional name. If it's not a function, we can't name it f of x or g of x or f inverse of x or anything like that, and we have to just leave it as y equals the cube root of x. So as we think about that one, I'm going to graph this one in green. Let's think of what's going on here. The cube root of 0 is 0, the cube root of 1 is 1, and now the cube root of 8, that's our next perfect cube, would be 2. So this graph, didn't draw that very well. This graph is going to look something like that. Going into the third quadrant again, the cube root of -1 is -1. The cube root of -8 is -2. And so now we're going to get this graph, more or less, that looks something like that. Now, I wish I'd drawn this a little bit better towards the center of this, of this graph here, and you could see in a little greater detail what's going on, but I think you guys probably understand what's happening. I tell you what, I'll open up my calculator here in just a second and we'll get a slightly better version of that graph. But while that's happening, let's go back and talk about this again. These two graphs here have a certain type of symmetry to them, and I'm thinking you guys have learned this over the last couple of years. It's not x-axis symmetry, it's not y-axis symmetry, but it's going to be symmetry with respect to the line y equals x. So let's see if we remember this from before. So let's see, I'm going to go here. Let's see, we're going to press menu. I'm going to go to a graph, and let's use the calculator to graph what we just came up with. So our first function was f of x is equal to x cubed. And the second function we came up with, let me hit tab here to get to that screen, and we are going to do the cube root of x. So I'm going to put a 3 right there for the index, and we'll put an x there. So all this really tells me is that the two graphs that we drew were pretty accurate, but now you can see in a little bit greater detail here exactly what happens near the origin. All right, these two curves, one in blue, the original, and then the new one in red, they appear to intersect 3 times. And those would be 3 spots where when you come up with a point that was on the original graph of f of x, and then you invert that point, you end up with the exact same coordinates that you had just a second ago. One of those, not surprisingly, is the origin at 0, 0. So let me go ahead and just plot that point right here and do a graph trace, and I'll put a dot right there at 0, 0. When we put in a 1 for x, we get the point 1, 1, and of course when we invert that, we're still at 1, 1. And then when we put in -1 for x, that gets us to -1, 1. So those 3 points in black there that are all labeled are ones that don't move at all when you invert them. As opposed to the point 2, 8, which doesn't really show up on this graph but is way up high here on the blue curve, when you invert 2, 8, that becomes the 8, 2 that you would see over there to the right. So what I'm thinking you guys probably remember is that the line of symmetry here between a function and its inverse is simply the line y equals x. And if you were to draw the line y equals x there on top of any functions graph and its inverse, you're going to see symmetry here, that if we were to take the original blue curve and fold it over that black line, it would match up perfectly with the red curve on the other side of it. Okay, so those are some things to notice right there. Last thing I want to point out, if I went back to a trace right here, everybody, and said, okay, we were going to trace on the first curve. Now, what I want you guys to notice is that as I go to right about here, the blue curve, the original, is in the first quadrant. At this point where I've got my cursor right now, my x and y coordinates are both positive. When we invert a first quadrant point, positive, positive, inverts, but it's still going to be positive, positive. And that's why its inverse also goes into the first quadrant as well. Likewise, if we move it way down here, now we're in the third quadrant where x and y are both negative. Well, when you invert a negative, negative, you end up with negative, negative, still in the third quadrant. And that's why the inverse of a point here would be over on the left somewhere, but still in the third quadrant. Think about what happens if you were to invert, let's say, a second quadrant point. A point right about where my arrow is located, guys, that would have a negative negative x coordinate and a positive y coordinate. Well, when you flip negative positive, when you invert it, you're now going to get a point that's positive negative, and that would take you down here somewhere into the fourth quadrant. And that kind of matches with the idea of reflecting over the line y equals x. So I'll go ahead and draw that in here, guys, that the line y equals x would probably look something like this. And obviously the calculator graph is a little more precise than mine, but that's essentially what happens. Okay, so with that in mind, let's walk through 4 quick examples, everybody, of how to find inverses of functions, and this is the important part now, stating if that inverse is a function or not. So let's talk about a linear function. I don't think this is going to give you any difficulty here at all. So f of x is equal to a 1/4 x plus 2, so we'll switch our x and our y and get x is equal to 1/4 y plus 2, and we'll solve that for y by subtracting a 2 from both sides. And then we're going to go ahead and multiply everything by a 4. And we're going to get y then is equal to a 4x minus 8. And thinking real quick, I'm not even going to spend much time drawing a really good graph here, guys. We're just going to eyeball this one. Thinking about what this looks like, the original function right here, 1/4 x plus 2, is going to have a y-intercept of 2. And a slope of 1/4. So we'd be going up 1, and then 1, 2, 3, 4 to the right would get us to this point here. So we certainly could do a fancier job with this, everybody, but I think that's probably good for our purposes right now. And now the question becomes, what happens when we go to graph its inverse? And I'll do that in red, actually, which is y is equal to 4x minus 8. Well, now our y-intercept has dropped way down here to 8, and trying to keep my scaling consistent here, everybody, which is kind of important. 1, 2, 3, 4, 5, 6, 7, and 8. Our y-intercept is way down here, but our slope is 4. So we're going up 4 units, 1 to the right, up 4 units, another 1 to the right. And this graph now is going to look something like that. So, wow, that's not a very straight line, Mr. Fontana, but hey, that's okay. All right, so that's where we're at in terms of the graph and its inverse. So, couple questions to think about. The first one, before we do anything else, does this seem to do what the graph of a function and its inverse should do, which we talked about a moment ago? Do we see symmetry with respect to the line y equals x? Well, of course, y equals x passes through the origin with a slope of 1. Up 1, right 1, up 1, right 1, and it would essentially look something like that. Now, obviously, I freehanded this graph and I didn't pay a whole lot of attention to what I was doing. But what should happen, everybody, is that every time, or every spot where an original function crosses the line y equals x, its inverse should cross through the exact same point. All right, we saw that back looking at the calculator graph here a second ago, where, boy, all 3 curves, the blue and the red and the black, all intersected at these 3 points here of 1, 1, 0, 0, and -1, -1. And even though I didn't do a great job of graphing this, I can kind of see that right about here, where the blue curve, excuse me, the blue line intersects the green line, yeah, I think I'm close enough to feel good about this, that the red line should have crossed through there as well. The second thing, though, everybody, is the inverse here a function? Well, as we'll get into checking in just a second with something that I think you guys recall called the vertical line test, I take that back, that's something we actually talked about earlier. The red graph, the red relation, does in fact pass the vertical line test as well. So we would say that this one right here, that yes, it is a function, and because it is, probably just leaving it with the name of y maybe isn't the best way to handle that. We're going to go ahead and rewrite this now as f inverse of x is equal to 4x minus 8. I don't think this is a necessary step, everybody, but it does say something important. It's saying that the inverse relation that we came up with just on the step above, where we called it y equals 4x minus 8, we're acknowledging that it is a function, and so therefore we've named it using function notation, which is f inverse of x. Now, if that relation was not a function, we would have just stopped at this line right over here, all right, and said, okay, we're done. But since it is a function, we're going to name it as a function, 4x minus 8. And just to make sure that we know what we're doing right here, I would ask somebody at random to pick a value that's in the domain of the original function right here. And it's probably good if somebody picked something that was a multiple of 4, because that's our denominator. So why don't we pick something like negative 12? And let's see what happens when we put a negative 12 into f. 1/4 of negative 12 is going to be a negative 3. Negative 3 plus 2 is going to give us negative 1. That's not anything earth-shattering right there. It's a linear function. Its domain is all real numbers, and its range then is usually all real numbers as well, so there's nothing unexpected. But now the question becomes, what happens if we take the inverse function and we use the output from f, this negative 1, as our input now into the inverse? So let's go back down here now, everybody, and see what happens when we plug a negative 1 into this function. The 4 times the negative 1 is going to give us negative 4, and negative 4 minus 8 is going to give us negative 12. And we end up right back with the exact same x value that we started with right here. This is what happens with inverses, everybody. No matter what value you pick, we chose negative 12, but no matter what value you choose as the input into f, if you take that output and now treat input into f inverse, you're going to get the exact same value here that you started with. That'll happen every single time. All right, let's do another example. The inverse of a quadratic function is not easy to find, much harder than a linear, and I'm not sure it's something that you guys have done before, but the good news is you do know how to get started. You switch your x and your y, so you're going to get x is equal to a y squared minus 4y and a minus 5. And we now need to solve this quadratic equation for y, everybody, which is not an easy thing to do. But if you recall, this is something that your author spent a decent amount of time talking about in section 1.2. Completing the square is the trick we're going to have to use now, guys, to get y by itself when you've got both a y squared and a linear y term. So to do that, we're going to bring the 5 to the left side and make that an x plus 5. I'm going to leave a little bit of room right there, and that's going to equal a y squared minus 4y. Now, if you recall, we said that completing the square can always be done. It will always work, but it's really only the best method to use when you've got an a value of 1 and a b value that is even. Well, as dumb luck would have it, that's what we have right here, everybody. So, otherwise we'd have to do some factoring, and there might be fractions floating around, and we'd all cry at night, and it'd be terrible. Anyway, let's start working on this one right here. We're going to take half of b, square it, and add that to both sides. Our b value is negative 4, so half of that is going to be negative 2. Squaring the negative 2 is going to get us a positive 4, and we're going to add a 4 to the right, and we're also going to add a 4 to the left. The reason I added the 4 on the left, everybody, instead of simply doing this, which we did earlier, we're actually trying to solve for y here, everybody. And so to do that, we eventually want to get things moved over here onto the x side. Okay, so the left side of the equation is going to become an x plus 9, and on the right, we've created a perfect square trinomial, and that's going to be y minus 2 quantity squared. And in case we haven't caught on to this just yet, everybody, the real benefit to completing the square is the idea that now there's just one y in this equation, not 2 the way that there were before, and that means that we can solve this with inverse operations. We'll start off by taking the square root of both sides. Now remember, guys, anytime you put a square root there, there needs to be a plus or minus in front of it. So plus or minus the square root of x plus 9 is equal to y minus 2, and then all we have to do is add the 2 on the other side. And I'm going to flip while I'm at it and make it y equals 2 plus or minus the square root of x plus 9. Now, that right there is our inverse. What remains to be seen as of yet is whether or not that inverse is a function, and if we can rename this now as, I called the original one g of x, so can we rename this as g inverse of x, or do we have to just leave it as y? So let's talk about this and kind of approach it from a couple of different angles, guys. Where do I have the most room to do this? I guess let's go back right here and see where we're at. Graphing a quadratic function, this is something we've had some practice at, maybe not a ton in this year, but you've done it a lot. Your vertex would be located located at negative b over 2a. This is your axis of symmetry anyway. Negative b over 2a. b was negative 4, so the opposite of that is 4. A is 1, so that's a 2. So we get x equals 2 for the location of our axis of symmetry here. And to actually find the vertex, we're going to take that 2 and cram it into G and see what happens here. So G of 2 is going to be, that's a 4 minus 8, that's a negative 4, minus 5, is a negative 13. So the original graph of G, I don't think I'm going to draw this very accurately, you guys, but I'll eyeball it, is going to have a vertex way, way down at 2, negative 13. So I'm going to guess that it's down here somewhere. This is a parabola that opens up. It's not fat or skinny, just kind of a normal one, and it does something like this. That's probably as accurate as we need to be right now. Let's talk about graphing the inverse that we just came up with, although I'm really hoping you guys remember what's going on here already. Okay? The inverse of a parabola, when you reflect it over the line y equals x, is still going to be a parabola. It's just going to be one that instead of opening vertically, opens horizontally or opens sideways. So as you're thinking about whether or not this inverse of a parabola is a function or not, you might already be able to answer that. Let's see what's going on here, guys. All right, so with this in mind here, let's take a look at what we are doing here. All right, guys, so we've got, let's see, a radical function right here of 2 plus or minus the square root of x plus 9. So if we think about where this graph would begin, that 2, even though it comes at the beginning here, is actually the vertical shift of what's happening within this function here, everybody. So what's going on there, guys? Give me just a second here. I just realized I goofed something up here, guys. When I went to go find G of 2, I wonder if you guys noticed this, that was a 4 and a minus 8 was a negative 4. The negative 4 minus 5 was going to give me a negative 9, not a negative 13, Mr. Fontana. So maybe I should shift this graph up just a little bit. I don't think that's going to change too much there, but that's our vertex. Sorry about that, guys. Now, and the reason that occurred to me is because I was thinking about this graph, and I was thinking about where we were going to start it from, and something didn't quite seem right to me. This 2, coming at the beginning of the function, is actually going to be your vertical shift. That's actually your k value. And your h comes from the radicand right here, and that's going to be negative 9. So this graph is actually going to begin from the ordered pair of negative 9, 2. All right, which you might notice then is the inverse of what we came up with right here. So just eyeballing here, guys, negative 9, 2 is going to be way out here somewhere. And then it's a square root graph, all right? So it's going to look something like that on the top, and it's going to look something like that on the bottom. And that, there you go in red, is going to be roughly the inverse of what we came up with there. So in asking the question, is this inverse a function? The answer to that pretty clearly is no. This sideways red parabola would fail the vertical line test. It would not, therefore, pair only one y value with each x value. And so for that reason, we're going to leave it written as y equals, and then we're going to go ahead and answer that no, this inverse right here is not a function, which of course we're kind of indicating right here by just leaving it as y. So I think in your homework they give you directions that say determine whether G inverse exists. And that can be a little bit confusing. I don't usually talk about it in those terms, but let me try to explain that right now. Every function has an inverse. However, not every one of those inverses is a function. So as we look at these two problems right here side by side, what do I want to do? That? No, that wasn't it. As we look at, where's my dual page display thing? There it is. All right. As we look at these two problems side by side, there we go. That's what I was looking for. Both of the functions in examples A and B, both of them have inverses, but only the first one in A has an inverse that is a function. So we would say, for example A, that f inverse exists, meaning that we can find it and it is a function. But then as we look at example B, we would say that G inverse does not exist. We can find the inverse of G, but it's not a function, so you couldn't name it G inverse of x. That is a little tricky, something that we've got to get used to here. So, okay guys, so we've done a linear function, we've done a quadratic function. I accidentally cloned that page, so let's get rid of that. This is one that people haven't dealt with a whole lot, and so I wanted to talk about it. Not that it's overly difficult, not that it's super applicable, but I thought it was kind of cool. The inverse of a rational function. Well, like always, people know how to get started, all right? So actually, you know what, before I do anything else, let's name this thing with function notation. This is a rational function, so it can be named that way. Let's go ahead and find the inverse. So let's switch things around. The y becomes an x. The x's, plural, all become y's. So 2y plus 1 over a 3y minus 5. So that was the easy part in finding the inverse, but now the question becomes a little bit tougher. How do we get y by itself to solve for y in terms of x? And this one can be a little bit tricky here as well. So let's get rolling to it. If you feel like pausing and thinking about this for a little while, go right ahead. I'd be proud of you. But we're going to roll on this one. First thing we're going to do, guys, the fractions are messy. So we're going to multiply both sides by the denominator, the 3y minus 5, and that means we're going to have some distributing to do over here on the left side. So I'm going to multiply both sides by 3y minus 5. Leave myself a lot of room there, okay. And the left side then is going to become 3xy minus 5x equals, that cancels out with that, and we get a 2y plus 1 over there on the right-hand side. Okay? At this point, if we're not quite sure what to do, it's never a bad idea to remember the overall goal. What are we trying to accomplish here? We're trying to solve for y in terms of x. So now what we're going to do is recognize that there are 4 terms in this equation and that 2 of them contain the variable that we're trying to solve for. We're trying to solve for y, so those 2 terms have it, the other 2 terms don't. So what are we going to do? We're going to collect our like terms on one side of the equation and get rid of everything that doesn't contain that like term. So check this out now. We're going to have a 3xy and a minus 2y is equal to a 5x plus 1 over there on the right-hand side. And now, guys, the magic step right here for how to get from 2 y's down to just 1 y is the F word. Factoring. And anytime you can factor in math, it is almost always worth the time and effort. We're going to factor the y out that these 2 terms have in common, leaving us with a 3x minus 2 in parentheses is equal to 5x plus 1. And there, everybody, is the one singular y that we needed. So we're now going to divide both sides by the 3x minus 2 and get y is equal to 5x plus 1 over 3x minus 2. So there's the inverse, at least written as it's solved for y there. It's just a question now of whether or not that inverse is a function. And I don't want to dwell on this too long, but something really cool happens here when you're graphing a rational function and its inverse. So let's discuss this one real quick. So I'm going to go kind of fast through this, everybody. If we were to graph the original function, h of x, which we have right over here, let me move this over just a bit. And the 2 things we should be talking about when we're graphing rational functions are vertical asymptotes and horizontal asymptotes. Vertical asymptotes occur when the denominator is equal to 0 unless there was a hole, and there's no factoring here, so there's no holes. So if we set the denominator equal to 0 and solved, we'd get a vertical asymptote at x equals 5/3. Not all that pretty. Horizontal asymptote, we would compare the degrees of the numerator and the denominator. They're the same. They're both a degree of 1. So our horizontal asymptote is going to be y equals the quotient of the leading coefficients of the numerator and denominator, so that's going to be 2/3. All right, so this is really messy, guys, and as I said, I'm not going to spend a ton of time on this, but we've got a vertical asymptote here at 5/3. We've got a horizontal asymptote at 2/3, and if I took just a little bit of time to think about where this thing would be located, like for example, if I put in a 0 for x into the h function and did h of 0, I would get -1/5. That one little point right there tells me that this graph exists in this lower left quadrant, and instinct tells me that it probably also exists in the upper right quadrant, but let's check that by maybe putting in a 2. H of 2 is going to get us a 5 on top and a 1 on bottom, so 2, 5, yeah, it's going to be up here. Okay, guys, so that in blue, roughly, is the graph of the original rational function. Now let's take a look at its inverse that we came up with right here, and I tell you what I'm going to do. I'll just write this right here. Okay, so what's going on here? With this function that we just came up, with this inverse, we're not sure if it's a function yet. Let's check our vertical asymptote first. What would make the denominator equal 0? Add the 2, divide by the 3, and we would get x is equal to 2/3. For a horizontal asymptote, once again, we would look at the leading the degrees, which are both 1, and then, because it's a tie, we would take the quotient of the leading coefficients, which is 5/3. And if you guys notice, these two asymptotes that we just came up with on the inverse are kind of the flip around here, the asymptotes that we came up with in the original function. That really shouldn't surprise you all that much, but that's kind of cool. So let's see what's happening next, guys. Let me go green here. And again, just trying to eyeball it, my vertical asymptote of roughly 2/3, so that'd be about there. My horizontal asymptote is y equals 5/3, so that would look something like that. And now, I guess I'm going to stick with, let me go back to blue here now, guys, for the graph of this one right here. All right, so picking a point just to the left of that vertical asymptote, which is 2/3, let's go ahead and evaluate with a 0 in here. And when we put in a 0, we're going to get a -1/2. I lied, I am going to go green. So 0, -1/2 is going to be just below that original asymptote, but right there. So focusing on everything in green, this graph is going to look something like this. And now putting in something to the right of that vertical asymptote, like maybe 1, when we put in a 1 there, we're going to get a 6 on the top, we're going to get a 1 on the bottom, so that's going to be the point 1, 6. That's going to be way up here, and this graph is going to look like that. Now there's a lot going on in that graph right now, guys, and the question I wanted to ask you guys is, does it look like the green and the blue might in fact be inverses of one another? Okay, and the answer to that, this isn't going to come out great because I drew it by hand. I like the way it looks over here. That point of intersection looks like it might very well be on the that line y equals x. There should be another point of intersection right down here, and I don't think I drew that one really well. Anyway, long story short, is the green graph a function? Yeah, it is, everybody. It passes the vertical line test, so we can go ahead and rename this inverse here as h inverse of x is equal to 5x plus 1 over 3x minus 2. And back to the question, the way they would phrase it in the book, yes, h inverse exists because we found it and it is a function. Last one of these that I wanted to do with you, I think it's the last one. Yeah, and this is actually one of the easier of all of them, but I just want to make sure everybody remembers what's going on here. With a trigonometric function like y equals sine of x, when we go to flip our variables and make this x is equal to, and I'm going to leave a little space on purpose, the sine of y, it's the same process now, the same thoughts. We have to try to get y all by itself. And the way we're going to do that is that we have to get rid of sine. Well, the way we get rid of sine is by taking an inverse sine, and I want you to think about that name, inverse sine, everybody, on both sides. So they were not very creative when they were coming up with the name right here. The operation that will undo sine, they simply called inverse sine. So those ones are going to cancel, and we're going to get y is equal to, and everybody don't think too hard about this, there is no way to simplify the inverse of sine. It's kind of its own separate operation and ratio all by itself. So congratulations, we're done with the inverse. When it comes to determining whether or not the inverse exists or the inverse function exists, let's think about what this would look like. Sine of x is a graph that I'm hoping you guys know well. 0, 0, let's see, 2 pi 0, pi 0, and then of course we have a peak here at pi over 2 and a trough at 3 pi over 2. Okay, and that graph is going to look something like this. That's not my best, but in fact that's pretty terrible. But anyway, oh, I lost the whole thing. All right, so it's going to do that and that and that and do something like that. When we go to take the inverse of this graph, we reflect it over this magic line y equals x, and now things get to be just a little bit weird. One thing I want to talk about, though, before we move on, and I haven't discussed this with any of the 3 previous examples, for the original function of sine of x, let's talk domain and let's talk range for just a second. The nice thing about sine and cosine, everybody, is that they have unlimited domains. You can take the sine of any real number using that as your angle. It doesn't have to be something nice or pretty. So your domain is all real numbers, as kind of indicated by the fact that this graph goes forever from left to right with no holes, no jumps, and no asymptotes that it has to skip over. Okay, so that's our domain right there, everybody. And now when we talk about the range of this function, the set of all y values, I'm hoping you guys remember this one as well, that the sine of an angle is never going to get bigger than its peak value of 1. And likewise, it's never going to get smaller than its trough value of -1. Well, now, when we go to try to evaluate y equals the inverse sine of x, remember that whatever number we are given to put in for x now, that isn't an angle, that's now the ratio itself. So you can answer the question, what is the inverse sine of 0? Because there is an angle out there, in fact, infinitely many, that have a sine ratio of 0. Such as 0, such as pi, such as 2 pi, and so on and so forth. But there are some questions with inverse sine of x that you can't answer. If I were to ask you guys, what is the inverse sine of 2? What I'm really saying is, give me an angle that has a sine value equal to 2. Well, that's impossible, because sine can never be more than 1, and it can never be less than -1. So, with that idea in mind, what I'm hoping you guys recall is that it's the domain here for inverse sine that's actually limited here. I'm sorry, I never went back and wrote the range down. For the original function, we know that y has to be bounded in between -1 and +1, and I am using brackets there, guys. Those are inclusive. Now, back to inverse sine of x, right down here, it's the domain that has to be limited in that same way between -1 and +1. But when it comes to the range here, the range is the set of all y values, and these are the angles that we're coming up with here. It's the range now, everybody, that's actually all real numbers. So, if we recall what this looks like, everybody, let's think about just a few points right here. We take the point 0, 0 that sine passed through initially, we invert 0, 0, and we still get the point 0, 0. Now, most people know that since the sine wave basically seems to ride the x-axis forever in both directions, the inverse sine wave is going to ride the y-axis forever in both directions. Okay? But people get a little bit confused as to which way it goes. What I'll see a lot of people do is they'll say, okay, I know this inverse sine wave goes here, and it's going to go here, and it's going to go here. But I'm not sure whether it does this or whether it does this. It's one or the other, and I'm not sure which. And so to answer that question, probably the easiest thing to do is to think, well, let me give you 2 options right here, is to think about a particular point, like maybe this one right here. And I'm hoping you guys remember that the first peak to a sine wave happens at pi over 2 with a y value or a sine value of 1. And if you were to now invert that ordered pair, it's now going to tell you where the first peak, quote unquote, of the inverse is, which is going to be at 1 pi over 2. And that's going to be roughly right about here. What's more important, I think, everybody, is the idea that as we drew the blue wave, this first hump was in the first quadrant. Positive, positive for your x and your y coordinates. Well, when you invert a first quadrant point, you're still going to get a first quadrant point, positive, positive. So that means it's impossible, you guys, to invert a first quadrant graph and take it into the second quadrant. That doesn't make any sense. But when you invert a first quadrant, you're still going to get positive, positive, so it's got to do something like this. Then as we get down here, you went into the fourth quadrant where your coordinates were positive, negative. Now when you invert those, they're going to go negative, positive. That's going to take us into the second quadrant. And then I think from there we can figure out everything else that's going on. All right, so it's a messy graph, everybody, but this does in fact meet that line of symmetry that we needed for the line y equals x coming right through there. Okay, one big concept left to talk about and then we're about done with this section, and that is the concept of one-to-one functions. This again is something that we can write the definition down for, but we're not always sure what exactly to do with it. So the test for a function being one-to-one, everybody, is this. For every y value in a function's range, there has to be one and only one x value in its domain. Now, if that sounds a little bit familiar, it should. That's really, really close to the definition that you guys learned of a function way back probably in Algebra 1. But it gets flipped around, gets inverted, if you will. For a relation to be a function, it has to be the case that for each x value, there's one and only one y value on the graph. But if that happens, and you are in fact dealing with a function, we might go further in terms of describing it and say that it's one-to-one if, for every y value, there's one and only one x value in the domain. That's what happens then for when a function is one-to-one. And the significance of this is what gets lost sometimes. If a function is one-to-one, then its inverse exists. That's the way your author would say it. I wrote it out here by saying then f inverse of x is also a function. So that's the significance, everybody, of a function being one-to-one. If it is one-to-one, then its inverse is also a function. If a function is not one-to-one, then its inverse is not a function. And let's just look at two quick examples to try to illustrate the difference right here. So first off, f of x is equal to x squared. Let's go with something nice and easy right here. So we've got a parabola opening up into the first and second quadrants, and it looks like that. First question, hopefully obvious. Is it a function? And the answer to that is yes, because it passes the vertical line test. For every x value, there's one and only one y values that's found in here. But the next question is, everybody, is this function one-to-one? Well, let's go back to the definition. To be one-to-one, it would need to be the case that for every y value, there's one and only one x value in the domain. And I don't know, I'm just going to throw out, and I know I didn't graph this accurately, guys, but let's throw out a y value right here of 4. And what I see, everybody, is that there's a point over here in the first quadrant that'll make y equal 4. The point 2, 4 exists on this graph within the first quadrant. But it sure looks to me like there's another x value right over here, negative 2, that would get us the exact same y value right there of 4. So what I see here is something that definitely is a function, but it would appear to me anyway, it would appear to me, everybody, that we've got one y value that has more than one x value. Now, if you might have pieced this together already, good for you. What's going on here, guys, is something called the horizontal line test. And because this graph right here fails the horizontal line test, we would say that it's not a one-to-one function. So let me go back to what we wrote down just again here, and the test for a function being one-to-one, I'm going to write HLT right there and hope that you guys understand that that means horizontal line test. If you don't, you might want to write it out. So this one right here, let's go ahead and write some stuff out. That f of x is a function. It has to be because we named it f of x, but the reason is because it passes the vertical line test. However, this thing right here, now let's go with it a little bit further, it now fails the horizontal line test. And therefore, as a result, we would say that f inverse of x does not exist. Now again, to be clear, this blue function does have an inverse, but that inverse is not a function. And as I think you can probably figure out pretty quickly, if I were to draw that inverse, which would be the sideways function there, if the blue function fails the horizontal line test, that means that the green inverse is going to fail the vertical line test. And that's why its inverse is not a function. So again, to be clear, you can draw the inverse. You can even come up with an equation for that inverse, but that inverse is not a function. And on your homework, your author is going to want you then, therefore, to declare that f inverse of x does not exist. Now, let's contrast that with what's going on over here on the right with g of x equals x cubed, which we talked about a while ago. So this graph is going to look something like that, and let's see what's happening. First of all, as I think is obvious right here, g of x, I probably should do it in this order right here. It passes the vertical line test. Okay, no vertical line is going to cross through there. Therefore, g of x is a function, which again we knew because they named it that way right at the beginning. But now, if we check this thing for being 1-to-1 and we draw a series of horizontal lines over this graph, what we can see here, and I think that's probably good enough to prove it to us, is that no horizontal line that we can draw would pass through that graph more than once. So we would now say that g of x also passes the horizontal line test. Okay, and therefore what we can conclude right there, we can make two conclusions then. Therefore, g of x is a 1-to-1 function. And the other conclusion going along with that would be that g inverse of x exists. Meaning that you can come up with the inverse of this and you can write the inverse as a function, which of course would be the cube root of x, which we did way back at the beginning of this lesson here. All right, so those two graphs right next to each other kind of, I think, illustrate the point of what's going on with 1-to-1 functions, and that's going to show up on your homework a little bit here as well. All right, guys, so that's a wrap on section 1.5. Hopefully that made some sense. Let's give the homework a try, and let me know if you guys have any questions on that.